All right, let's talk about LC circuits. This one is not as long, so I'm not going to speed it up, just in case you guys need to uh, copy things down, especially since the inductor review that was a review is new. Okay, so an LC circuit, as it implies, is an inductor with a capacitor, and of course I'm left-handed, so my hand covers the whole page, but whatever. Okay, let's say you have this capacitor, and it's charged to the top. The circuit is open. Okay, so no currents flowing through yet. Okay, the inductor has some inductance L. The symbol, the circuit symbol, is kind of like a swirly line instead of a jaggedy line. The jaggedy squiggle is the resistors, right? Okay, so capacitor starts with some charge, and so let's say you close the loop. When you close the loop, you get a current, um, but that change in current, the inductor originally had zero current in it, so now it has current going through it, and so it'll have some potential. And that potential for the capacitor and the inductor is given as I'm writing it. And so again, it's a closed loop. So you want to use Kirchhoff's loop rule, and so the sum of the voltages around your loop should sum up to zero. The In the direction of the current, the capacitor is a positive potential, whereas the inductor is a negative potential. So seeing how current is a rate of change of charge, that charge is coming from the capacitor, and so a positive current is a negative change in charge. And so when you substitute that in, you get a second rate of change in charge with respect to time. So actually, there's a mistake there. That should say d squared q over dt squared. There should be a squared on the right hand side. Anyway, in the red pen, it's written correctly and rearranged in such a way that if you notice, it is a second order time rate of change of q relating to q itself. And we've done mathematical equations like this type of differential equation. It's a second order one, and we did it when we did springs. And we also did it when we did pendulums. So if you compare them and you look at the coefficient in front of your first order term, in front of the x or in front of the s for pendulums, that's the arc length, right? We made approximations so that we could write it in that way. They each were sinusoidal. They were simple harmonic motion. And so, since the mathematical structure is the same, um, you'll see that LC circuits actually behave kind of like um, harmonic oscillators. You'll have current go through, max out through the inductor. The inductor will uh, have a maximum rate of change. No, it'll have maximum current, minimum rate of change, and then it will, as the current starts to die out, then you have an increasing rate of change, and then that inductor potential will increase in the other direction, right? So you end up with a kind of oscillatory uh, current where the capacitor will discharge and then charge in the opposite direction and then discharge back, and so it'll keep switching back and forth. It will oscillate. And so if you look at your frequency, your natural frequency of this inductor or this LC circuit is square root of 1 over LC. So it's basically just dependent on your uh, inductance and your capacitance. This natural frequency, which means it influences your period, it influences your frequency, the regular frequency in which it flips back and forth, and so on and so forth. And so plugging all that back in, you can find the relationship between charge with respect to time and also current with respect to time. And you'll notice that since your current is the derivative of your charge, um, while your charge will be a cosine, your current is a sine. That means that it is out of phase. It will be 90 degrees. Your current will lag your charge by 90 degrees, or in terms of time, pi over 2 omega.